let us now see then, if the work done for conservative forces, so I am focusing on conservative force, if the work done is independent of path 1 to 2, which is equal to integration f dot dl from 1 to 2, then I can write this as the difference between a quantity at these 2 points. I will interpret this in a minute, but for the time being let me call it the potential energy. Recall from your course in thermodynamics or the first law of thermodynamics in your 12th grade that a similar quantity, the internal energy, is defined in first law because the difference of the heat and the work done by gas is independent of the path taken on PV diagram. Similarly here, if the quantity f dot dl is independent of the path taken, it can depend only on the endpoints, and therefore I can write this as a difference f of this quantity. I am calling this potential energy. How is it related to the force? We just saw that I defined it as f dl is equal to minus from R1 to R2 as minus u R2 plus u R1. Therefore, for a small difference delta u is going to be f dot dl with a minus sign. The way then I interpret this is that the change in potential energy is the work done if I move a particle by applying a force opposite to the force field in which it is moving. For example, if I were to move it in a gravitational field, I will keep it in balance by applying a force opposite to the gravitational field. That is what this negative sign indicates. And the work I do, not the force field, but the work I do in moving the particle is equal to the change in the potential energy. That is the interpretation of potential energy. So, potential energy is equal to the work done by the person who is moving it in moving a particle in a force field, and I am moving it slowly so that there is no change in kinetic energy or anything, keeping it in balance all the time. So, let us see, if I apply the work energy theorem to this case, what happens? Let me again write, I am talking about conservative forces, then f dot dl I have defined as minus u r2 plus u r1 when I am going from point 1 to point 2. This by work energy theorem is nothing but Ke at point 2 minus Ke at point 1, and this is going to be equal to minus u at point 2 plus u at point 1, and if I reshuffle, I immediately get that Ke at 2 plus u at 2 is equal to Ke at 1 plus u at 1. I call this quantity kinetic energy plus the potential energy as the total mechanical energy. And as a consequence of the work energy theorem and the conservative nature of the force, I get it that in conservative force field, the sum of the kinetic and potential energy, and therefore the total mechanical energy remains a constant. You see, at 1.1 is the same as at point 2, and therefore it's same as 0.3, 0.4 and so on. This is known as the law of conservation. Energy. So let us see what we have seen so far. We have seen that I can define the kinetic energy as equal to 1/2 mv square, work as F dot dl integrated over, work may be path dependent, it may be path independent. This I call non-conservative force and this is conservative force, and if it is conservative I can define a quantity called potential energy. Actually I should really say it's the difference in potential energy which is defined as U R2 plus U R1 is equal to F dot dl between 1 and 2, and we saw that change in the potential energy at a position is equal to minus F at that point times dotted with dl. And for conservative forces, Ke plus U is a constant. The two key concepts that we have come up in this discussion is work, energy theorem, and conservation of total mechanical energy. Before their application and discussing more about them, I want to spend some time to get a feel for the potential energy. I define the potential energy as U R2 minus U R2 plus U R1 as integral F dot dl from R1 to R2, and I am not writing any path in this because this is defined only for those forces for which the work done is path independent. If you write it like this, you see that the change over a small distance is equal to minus F dot dl, and that gives you the interpretation of potential energy as the work done by you, by the external agency, to move a particle slowly in the external field. Also notice that it is the difference in the potential energy that has meaning. The usual practice is that you take a reference point R1 and put the potential energy to be 0 there and define the potential energy at all other points with respect to that point. Let us then take two examples for this. One, the spring. System in which if a particle is displaced by distance x from the equilibrium position, the force F applied by the spring is minus kx, and therefore if I were to calculate u x2 u x1 minus u x2 plus u x1, this would be equal to F dx from x1 to x2, or according to our interpretation, the difference in the potential energy from point 1 to point 2 is going to be the force is applied by me, so minus sign f dx from x1 to x2, which then becomes u x2 minus u x1 is equal to integral k x dx from x1 to x2, which is equal to half k x2 square minus half k x1 square, the formula you are well familiar with. Also, I take in this case u at x equal to 0 to be 0, and that is my reference point, and therefore I write in general ux is equal to 1 half k x square. Also from this, the force is given as du dx by definition, and this you see comes out to be minus kx. Let me elaborate a bit on that, because I did it in 3 dimensions. We had f dot dl is equal to minus u r2 plus u r1, and therefore for a short distance I had f dot dl with a minus sign is equal to delta u, and in 1D that will give me f equals minus du dx. Let us take another example, that of gravitational field, in which the force F as a function of r is given as minus g m m over r square. So, if I were to calculate the potential energy at a point r2 with respect to r1, this is going to be minus f r, and I move the particle along the radial line from r1 to r2, and this gives me integral g m m over r square dr from r1 to r2, which is equal to minus g m m over r r1 r2, and therefore I get u r2 minus u r1 as equal to minus g m m over r2 plus g m m over r1. In the case of gravitational field, I take u reference point at infinity, so u r1 at infinity to be 0, and that defines my u uniquely as minus g m m over r. You can again see that the force in the radial direction is going to be minus du over dr, which is minus g m m over r square. So far, you notice I have been focusing on one dimensional cases, and that is because the work done or the energy, whether kinetic or potential, are all scalar quantities, whereas the force and the displacement are vector quantities, and the two are related by this dot product, which becomes quite easy to work with in one dimensional case. For 3 dimensional cases, I will talk about later. We have special techniques to check things out. So, from now on I am going to concentrate on 1D case and talk about energy conservation in one dimension. As I had mentioned in the beginning of the lecture, that a motivation to develop the conservation principles of linear momentum and energy is to make solutions of problem easier.